Hi, I'm Miss Hall,
Hi, I'm Mr. Sajak.
and this is lesson 92, Hypotheses. These.
Please.
Analyzing hypotheses. In statistics, a hypothesis is a claim about a characteristic of a population. Here are some examples. 1. A drug company claims that patients using its weight loss drug lose an average of 24 pounds in the first 3 months. 2. A medical researcher claims that the proportion of U.S. adults living with one or more chronic conditions such as high blood pressure is 0.45 or 45%. To analyze a hypothesis, you need to distinguish between results that could easily occur by chance and results that are highly unlikely to occur by chance. One way to analyze a hypothesis is to perform a simulation. When the results are highly unlikely to occur, I can't say it.
The hypothesis.
Probably false.
Okay, so this can be a really confusing lesson because often it deals with some individual measuring whether or not their event is likely to occur, and then comparing that to a bunch of simulated events, and then graphing those simulated events. And because they're simulated, they'll be somewhat as a bell curve. Our job right now is basically to figure out, is the event that we are thinking about, the hypothesis, is that a normal event within a fair distribution of our bell curve? And basically what we're going to look at, as Ms. Hall draws a bell curve here.
So that's the simulation of many times of this thing happening. We're going to expect a normal distribution.
Yeah, so we've simulated this event happening over the course of time, and the proportion of the thing that we're looking at, how many times does it occur, and we've graphed those proportions, the number of times those proportions occur. And that's
You'll see this more in example 3. This is just an overview.
Yep. And so right now, if we fall within the meat of the bell curve, kind of the big hump part, and I'm using very loose language right now, that'll be more defined later. If we fall within there, then the event that we're looking at is likely. And if we fall towards the tail end of the bell curve, on either side, that event is unlikely, which that part at least should make sense. Unlikely?
Yeah.
It's unlikely. Example 3, analyzing a hypothesis. You roll a 6-sided die 5 times and you do get an even number. The probability of this happening is 1/2 to the 5th. 1/2 because that's the chance of rolling an odd or an even. So you suspect this die favors odd numbers. The die maker claims the die does not favor odd numbers or even numbers. In other words, it's a fair die. What should you conclude when you roll the actual die 50 times and you get A, 26 odd numbers, and B, 35 odd numbers?
Okay. So we're going to put those numbers on hold for a minute, in that we're going to analyze a simulation histogram of this event happening many, many times. So rolling a die 50 times, happening 200 times.
So in other words, I'm going to roll a die 50 times. That's one simulation. I'm going to roll the die 50 times. That's our second simulation. I'm going to keep rolling the die 50 times until I've done 200 simulations.
And this is a fair die.
Right.
This is not the manufacturer's die that we're testing to see if it's fair.
So in other words, we're getting a computer to do this. We're not actually doing this with a real life die, just what could happen.
And you expect, theoretically, when you roll a die 50 times, that half those times it's going to be an odd number. But in real life, and the simulation is going to try to simulate that, it's not always going to be 0.5. Sometimes it's going to be 0.4 or 0.52 or 0.6, and occasionally maybe it'll be 0.7, but that won't happen very frequently.
Yeah, so there are a lot of it's in there. So just to clarify that language, the percentage of times that we get an odd number out of those 50, we expect around 50%. But in real life, like Ms. Hall was saying, we don't, like 50% will happen sometimes that we get 50% odds. But other times we'll get between, 40 to 60% odds. Sounds reasonable. but that's what the simulations are for. It's going to look at and identify what is a reasonable percentage of odds to roll. So let's go ahead and look at the graph down below.
Do you want to write on it?
So if you're looking in this region here, where it says 0.50, this is representing the percentage of time out of the simulations that we got exactly 50% odd. So we got exactly 50% odd. This is a relative frequency. It looks like about 0.12 out of the 200 times. I didn't say that right. 12 out of 200 times. No,
it's 24. Right.
Yeah, it's 24 times. Because,
can I write this right
yeah.
here? So I think this is more than 0.12, but we're going to estimate right now at 0.12. This means this happened 24 times. To get a relative frequency of 0.12, you would take 24 times this happened out of 200 total times and get 0.12.
Yep. All right, so we can see each of these bars represents an approximate number of times that we got that percentage of odd numbers. So if we're looking at rolling 26 odd numbers, that's roughly what percent? 26 out of 50.
Double it.
Right, it's 52%. So that's this bar.
Are you already answering the question?
Here, yeah.
Okay, I'm not quite ready to go there. What we want to see here is that this is roughly a normal distribution. And on the side, in the interpreting math results, it claims that if you ran the simulation more times, it's going to look more and more like a normal distribution curve. So it's roughly modeling this. And like we drew in the first part of this lesson, I'm going to kind of cut off
the meat of the bell curve.
Right. We're going to get more precise with our language as lessons go on. But right now, this is the big chunk of the bell curve where most of the simulations, the results of most of the simulations were. So if when we roll this manufacturer's die, it lands in the meat of the bell curve, then it's probably a fair die because it matches where we think a fair die will land. These simulations that were run were done on a fair die. With our one simulation, or not our one simulation, our one set of 50 times is with the manufacturer's die that we're testing to see how does it compare to what I would expect a normal fair die to do.
Just to point that out, our die rolling is not on this graph, right? This graph only represents the computer simulations of a fair die being rolled.
Okay, so now we're going to say, okay, so if I got 26 out of 50 when I rolled the manufacturer's die, which is 0.52, I wouldn't say percent of the time.
No, 52% of the time.
52% of the time. Let me compare that to what I expect in a normal distribution curve of a fair die being rolled.
So we'll look at our graph.
Right, and you already highlighted it here. And that occurs in the meat. That is something we would expect to happen with a fair die.
So if it occurs with a fair die and it occurs with our die, we would conclude that our die is likely fair.
So the hypothesis is true. Can I say that?
For part A. Okay. It's not clear what the hypothesis is in this problem.
The die maker claims the die does not favor odd or even numbers.
Okay, so the hypothesis is the die does not favor odd or even numbers. Mm-hmm. In which case, if it's part A, then that is true.
Okay. Is there anything else you would write for this part?
I would write this is likely a fair die.
Okay. Okay. But part B, now this is a separate die, right? So we're checking in part A. It was one of the manufacturer's die.
Yeah, this first manufacturer's die is good, or we think it's good. It's likely that it's fair. Now we're testing their second die, and when we tested their second die, we rolled it 50 times, and we got 35 odd numbers. So what percentage is that of odd numbers? 35 out of 50 is 70%. So when we look at our graph, which again, the graph does not have these results on it because the graph was a simulated experience of a fair die. When we look, we see on the right-hand side of that tail of the bell curve, we see where 70% occurs. That is a highly unlikely event. So our hypothesis is false in this case. And statistically speaking, we put that it's probably false. Right, and I would justify that this is a highly unlikely event because it falls outside of the normal distribution curve, or at the tail of the normal distribution curve.